Thanks for the overview there, Eric. So as we set out to develop this platform, we wanted to adhere to certain principles. Number one is, use what you've got where it works. Don't reinvent the wheel. So we took a look at the requirements in Orange County at the RFP phase of the project, Sitka and Geosyntec, and said the requirements for condition assessment and asset inventory are very similar to what's going on in Lake Tahoe. So let's propose to leverage that. We know in this day and age, having a web-based tool to enable collaboration and support work both at the desktop and in the field is really the preferred direction for these types of collaborative data sharing platforms. And then we wanted to get momentum and get value in the hands of the users as quickly as possible, kind of bringing over the asset inventory and condition assessment functionality and getting that up and running right away as we work to build out the modeling and quantifying benefit components, which we're going to take more time. And then we wanted to stick to this model of making the technology available to anyone who wants to use it, as these are publicly funded investments that are oftentimes siloed to the funding base that creates the work and not frequently shared more broadly. And we see common challenges with common solutions and are looking to share knowledge and share patterns across agencies to pool resources and ultimately drive down the cost to receive the benefits of these types of platforms. So starting with a modular component, we have built out initially the inventory module for determining the location and type of structural BMPs that exist, identifying the regulated land development projects, are called water quality management plans, or WQMPs in the Orange County vernacular, in the South County permit language, but you could just think of these as parcel-based BMPs, and then the inspection and maintenance logs tracked through the inventory module. And then we added the ability to manage your delineation, the water that's draining to your assets, either directly through the web interface or by uploading or importing delineations that are maintained externally, for example, in ArcGIS, and implemented some tracing functionality to walk through your stormwater network and see how assets connect to each other and how the water flows through the system. And then we built on what we call the trash module to comply with the California trash regulations, which includes workflows for on-land visual trash assessments, OVTAs, assessment of priority and alternate land uses under the California trash regulations, and then some interactive map dashboards to track progress towards trash reduction goals. And then most recently, we have built out the modeling module, including the modeling parameters and inputs, web-based calculation engine, and summary reports for calculating water quantity and quality, load reduction, and volume estimates live within the platform. I'll walk through each of these modules, starting with the inventory module. We'll go through some slides just to set the context of these tools, and then we'll move on to the interactive demo. So within the inventory module, you can choose what type of BMPs you have and want to record in the tool. The definition of the BMPs can be defined by an administrator in the platform up front, and then you would inventory your BMPs and assign them to a specific BMP type. You can choose which assessment factors matter to you when you're prioritizing your assessed BMPs. There's maintenance tracking and the ability to upload design and O&M documents and to track funding. There's a data entry, and here's an example of the data entry and mitigation for a structural BMP with forms where we'll show the permittee experience. The foundation of this is web-based data entry. It's very clean interface, and it identifies both required and optional inputs. And as you might guess, standardizing your data here is key. Coming in the permittees, Eric mentioned there's 34 co-permittees having data in many forms, paper forms, GIS, spreadsheets. So we needed to provide a lot of data migration options to bring existing data into the system and kind of match this format. Once the existing legacy data is loaded, the data can be largely managed either within the tool through forms like this one or through periodically uploading and syncing your external data sets. So we have a bulk uploader, for example, to allow bringing in a spreadsheet of parameters and really wanting to make the transition into this online platform as easy as possible. And then we had, for the field assessment components, the field workflows for inventory enhancement, visual assessment, and maintenance tracking. Need to support a wide variety of workflows for the different user roles, working in both the desktop and in the field, and allowing both internal agency staff and contractors to upload their BMP assessments. The field workflow includes options to update inventory information, such as the BMP ID, the location, to visually inspect the BMP, and to record maintenance activities. Then from the maintenance and inspection information, we're able to calculate an assessment score, a rapid assessment score based on visual observations, and set benchmarking thresholds and weights for each parameter. So for example, in this case, looking at this particular type of BMP, in the field, you would observe the condition of the inlet and outlet, whether the device is operating, if there's any nuisance conditions, and then these are kind of yes, no type observations, and then a quantitative assessment of how much material is accumulating within the BMP. From these parameters, the module will calculate an overall condition score from 1 to 5 that can be used to weight the effectiveness of this BMP at reducing, performing its function to reduce load. And this is helpful to allow prioritizing permittee responses to when does a BMP need to be maintained and how much load reduction might this BMP be including. So that was kind of a quick overview of the inventory module. Next, we have a delineation map and workflows. This is a web-based view to visualize your network, your sub-basin network. In this case, the network is maintained by the OC survey department and then synchronized into the platform through web services. This defines the overall drainage patterns to both what we call centralized BMPs and to the distributed BMPs. The centralized BMPs are those that cover wide regions and kind of think of it as area-based treatment, and then the distributed smaller scale BMPs. The drainage areas to a BMP can be managed in several different ways. You can delineate within the web application by drawing a polygon of the delineation area. You can upload a list of catchments that are maintained within ArcGIS, or there's functionality to automatically calculate your delineation by tracing upstream from your digital elevation model. Different permittees are starting from different places. If you've been maintaining your asset inventory in GIS for a long time, you're not going to want to redo that. So a lot of permittees like to just upload their existing delineation inventory and continue to maintain it externally, typically in ArcGIS. If you're starting from scratch and you don't have your delineations well-defined, relying on the auto delineation through the DEM, digital elevation model trace, is a great way to get started and have your delineations built up front. And then over time, as you're adding new BMPs or potentially in the future planning scenarios for future BMPs, you might be satisfied just drawing them in the tool by placing vertices on the map. And then lastly, the WQMP, or the parcel-based development. These are new development and redevelopment that may have multiple BMPs on a site. In the map here, you can see where, rather than necessarily tracking every individual catch basin or downspout within a private development, which would be hard to inventory and may not be necessary, we can simply identify the parcels that have a control and capture the relevant parameters for at the parcel level. Next, I'll talk about the trash module, which was the module that was built for track permittee progress towards Orange County's trash requirements. The trash module utilizes reference information provided by the jurisdiction, the priority land uses, those commercial, high density residential and industrial land uses that generate the most trash load. And then some alternate land uses where jurisdictions may choose to perform a control if they can demonstrate that control of trash on the alternate land uses would produce a greater benefit than control on the priority land uses. The trash module allows inventory of new trash capture BMPs and addressing the trash capture attributes of existing BMPs, and then performing the required field assessments of visual inspection of trash loading. The trash module has a spatial calculation engine that overlays these inventories and land use layers and field inspections, mashes the layers together, and summarizes various markers of progress towards reducing trash load to the receiving waters. Here's an example of the online visual trash assessment, the OVTA workflow, where a user walks a transect. The pink markers here show a user in the field capturing a location from their tablet. They can take a photo, walk along the line to the next location, take a photo, record a score. For folks outside of California, the OVTA scores are an A, B, C, or D based on the amount of trash that's visually observed to accumulate, and record those observations. The tool kind of facilitates the first time you visit a site, you'll define your transect. The second time you come to the site, it'll remind you where you walked last time, so you can have a consistent assessment for future visits as you're looking to track trends over time. Then all of this information is summarized into a web-based map where you can view progress through a kind of a high-level manager's dashboard, showing the acres in your jurisdiction that have trash capture in place, how much area doesn't need trash capture because it's an A, it scores well in the visual assessment of trash. And then total progress, in this case, the city of Tustin here in this sample is showing 1,400 acres of full trash capture or equivalent out of 2,100 acres that they need to get to. And this allows prioritizing areas where you might need to visit to get closer to that ultimate future full trash capture. So that's a quick overview of the trash module. We can, if we have time at the end and there's curiosity about that, we can do more of the trash module. But what we really wanted to focus on today was the modeling module. Austin's going to talk about this, so I'll let Austin start chiming in and work to keep the slides in sync with Austin.
Yeah, thanks, John. Did my audio come on correctly?
You sound loud and clear.
Great. Hey, so as you said, we're gonna be talking the next few slides about our modeling module, and we're gonna start off with some of the requirements that we had as we set forth to build this system out. So for compliance with our permit, we're really interested in characterizing the long-term expected performance of our BMPs and the load reductions that we can take credit for. We're also required to quantify these benefits for both dry weather conditions and wet weather, stormwater conditions. So people are really familiar with stormwater controls, but in this region, we also need to control things during between event periods, that like managing irrigation runoff. That's what dry weather conditions are meant to describe. The system also needs to be fast enough that it can be run on the web. We want these systems to stay in lockstep with our BMP inventory. So when our users change things in the inventory or add a new BMP or refine a delineation, our tool needs to be able to recompute a whole new set of results for that BMP and for perhaps downstream BMPs that would be affected by an upstream change, and do so quickly enough to be responsive for a web tool. So how do we do that for an individual calculation? So here's the obligatory process diagram that webinars like this will always have, but we're going to walk through the calculation here. So the system starts with the set of components that John has already laid out. We've got BMP attributes. We know where these BMPs are situated in our watershed. And by now they've got a delineation, a shape that defines their tributary area. We're going to combine this set of information that Orange County Stormwater Tools manages with the resource we have with Orange County Survey. They manage a set of GIS web services. So by sending our delineation feature into one of these GIS services, we can produce a set of HRUs that describe the land surfaces contained in that delineation. Now, HRU is an acronym, stands for Hydrologic Response Unit. If you're, these units tell us information about the slope and the soils and the land use and the imperviousness. And this sort of set of keys, these HRUs, let us relate the land surface to some detailed hydrologic models that we've prepared in the background. So this lets us calculate the dry weather flow rate that's going to come off of this delineation, and to accumulate the stormwater runoff from some calibrated regional modeling that we've done for South Orange County. So after this step, what we have is our establishment of the hydrology of our delineation feature that's going to drain to our BMP. So this information can also be combined with regional monitored information to establish the loading that's going to enter the BMP as well. So our HRUs are really driving the hydrology, and they're driving the loading that our BMPs are going to receive. So now that we've got our loading from our delineation, we can route that through a BMP and transform that volume and that load by the processes that happen in stormwater controls. So for describing our BMPs, we'll leverage the set of attributes that we've recorded in our inventory and bring those forward. But then we'll combine those attributes to scale and size our BMPs according to additional modeling that we've sort of cached in the background here, with long-term capture nomographs for BMPs of various sizes and design features. Our nomographs consider different drawdown times and different BMP volumes at different sets of compartments like media and gravel storage and infiltration. And then we can also use functional curves that are built of local monitoring and of data stored from the International BMP database. And the advantage this gives us is that we can have a robust relationship between a BMP's influent concentration of a particular pollutant of concern and the effluent that we would expect to see from that BMP. And so with these fast lookup tables and functional relationships, we can transform our influent volume into our treated effluent volume for each node, and then move to the next downstream location and repeat the process. So in order to repeat this process in the right order, we've got a regional subbasin network managed by Orange County Survey that covers our entire region of interest of South Orange County with neighborhood scale, 40-acre scale subbasins. And Orange County Survey manages the relationship between these subbasins. So what they're doing is linking one subbasin to the next downstream subbasin. So if we can traverse this list of connected watersheds and solve each feature inside these watersheds in the right order, we can accumulate the benefit in the entire watershed and report those benefits at every node. So one more, there we go. Now we can see how each of these regional subbasins relate and how we can accumulate the load reduction benefit at each node in the watershed and march our way downward toward the ocean. So in the next slide, we're gonna zoom out here and look at the overall architecture and show how it helps us to achieve our quantification of benefits objectives here. So on the left-hand side, we see all the components that change frequently, like editing or adding an inventory item, BMP, or changing a delineation boundary and the associated recomputation of the HRUs needed for us to solve it. And on the right-hand side, we have our modeling input information. These inputs are editable, but are only updated periodically to represent our best available modeling data for our region. So these references are meant to be stable enough to provide a basis for our regulatory compliance reporting. But these two sides working together and communicating via our web protocol, passing the questions formed on the left with the modeling engine to get a result and answer. These two components working together gives us a stable and defensible, easy to manage and always up to date system for reporting our results and presenting them to both our users and ultimately to our to the regulator. So let's go to the next slide. So that's all great, but what do our users actually need to do in order to get this information reported back? All of that's fairly complicated. So what's the whole realm of information that a user would need to do to get a good result back for a BMP in their inventory? So we have up on the screen, this is actually a snip of the actual site. So to express an infiltration trench, for example, we start with the basics, the name, location, owner, jurisdiction, and a small set of physical attributes. So this infiltration facility really only requires 3 parameters to be entered by the user. In fact, the tool supports over 20 BMP types, and there's only between 2 and 5 required parameters for all of those types in order for us to be able to quantify their benefits with the system we have in place. So once we've got those attributes, we also need that delineation, of course. So the other thing that we have is the user would draw the delineation, and the tool will report to them the land surfaces and the acreages and imperviousness associated with those land surfaces right there on the BMP detail page. But recall, I was talking about HRUs before. These are all sort of saved in the background and referenced by the modeling module in the background, and that complexity is calculated, but it isn't surfaced for the user to have to worry about. And then every 30 minutes, the system will collect all of the changes that have occurred in the previous 30 minutes and recompute the watershed, recompute the whole network to keep the network in sync. And the results of that recomputation are presented on the BMP detail page and are here on the right-hand side, where we have a water balance on the top half and a pollutant load reduction in the bottom half. And we're able to summarize all of our results by wet and dry condition, and of course the overall total. So this brings us to an opportunity to go see what this tool looks like in action.